T-minus 4 minutes. The final closeout of the liquid oxygen and fuel load has begun for Booster 19. The objective today is a 10-engine static fire. This is the first time the foundational version 3 booster architecture has ever sat on the pad, putting a massive amount of new hardware at risk. In the traditional aerospace industry, a failure at this stage is viewed as a disaster. The standard approach is to move slowly, using years of planning to avoid any damage to the vehicle. Elon Musk's Beijing requires the opposite. He is building a fully reusable system, massive enough to transport the people and payloads necessary to establish a permanent presence on the Moon and Mars. This ambitious scale is only possible through iterative testing. Attempting to build the final, perfect version of Starship on the first try was a risk Musk believed would bankrupt the company before they ever reached orbit. To maintain financial stability, SpaceX had to break that ultimate vision into smaller, commercially viable pieces. These building blocks began with the Falcon 1 and the Falcon 9. These rockets allowed the team to learn the fundamentals of orbital flight and reusability on a smaller scale. Falcon Heavy was the final major stepping stone. It proved they could manage high-thrust, multi-engine systems, teaching the team how to build rockets their own way. This brings us to Starship version 3. It is a clean sheet design that uses the lessons from the first two versions to directly address recurring performance and reliability issues. But because this architecture is so new, the engineers have only seen it operate in computer simulations and fluid models. To prove the design actually works, they have to move past the models and risk millions of dollars of hardware in a real-world environment. At T-minus 40 seconds, the vehicle is on its own. All attention shifts to the heart of the booster, the Raptor 3 engines. SpaceX engineers designed this engine using data gathered from the production of roughly 600 previous V2 units. This diagram shows the result: extreme consolidation. They integrated the complex exterior plumbing of previous generations into the core of the engine. Removing these parts makes the engine lighter and significantly faster to build in high volumes. This simplification does more than just lower the cost. By reducing the total number of parts, they have stripped away hundreds of potential points of failure, increasing the reliability of the entire rocket. The countdown ends and the 10 engines ignite. This test is designed to reach the highest chamber pressures ever seen on a SpaceX vehicle. But at exactly T plus 2.135 seconds, the test comes to a sudden halt. A pad-side abort command shuts the engines down. Sensors on the diverter detected a manifold pressure lower than expected. The flight software identified the deviation and triggered a fast shutdown. SpaceX operates on a philosophy of extreme paranoia. They program their automated systems to trigger a full shutdown the moment a data point suggests a future failure, sacrificing the test to prevent a disaster. This safe abort stands in stark contrast to previous tests, like the catastrophic explosions that destroyed Booster 18 and Ship 36. When a rocket explodes, it often takes out the launch pad infrastructure with it. Repairing that damage can take months, which stops all vehicle testing and stalls the entire program. And that makes this abort a victory. By saving the pad and the booster, the team gathered vital data on real-world vibrations and engine performance without stopping the production line. This single aborted test is part of a much larger rapid integrated test campaign. This is the same strategy that turned the total failure of Starship's first flight into the hardware improvements that redefined the launch tab design. The results of this methodology are clear. Flight 2 achieved stage separation. Flight 3 completed a boost back. Flight 4 executed a water landing. By Flight 5, this aggressive testing led to one of the most significant milestones in aerospace history, catching the booster mid-air with the launch tower. Every failed test and aborted countdown provides the fuel for this progression, moving the program from early anomalies to mission success. Many observers believe that reaching commercial airplane levels of reliability for a rocket of this scale is impossible. The SpaceX counter-argument is that they aren't breaking the laws of physics, they are just relentlessly leveraging them. Establishing this engine reliability is the first step toward propellant transfers in orbit. Moving fuel between ships in a vacuum is the core technology needed to enable deep space missions. Perfecting that capability is what will allow Starship to put humans back on the Moon. Beyond that, it enables the ultimate goal of the program: sending the first crews to establish a city on Mars. Every terrifying abort and damaged engine is a necessary part of that journey. It is the price SpaceX pays to make